Okay, hello everybody. In today's video, we are going to be talking about topic 1.5. There's a lot of information in this. Some of it is applying old stuff to new polynomial functions. Others might be completely new, okay? But the nice thing about this being on a video is you can slow it down, you can rewatch it, you can do what you need to do to get a better understanding of this material. So the first thing we're going to talk about is the fundamental theorem of algebra. There is this theorem, a well-known theorem. You don't have to know the name necessarily, but that says if you have a polynomial function with a degree greater than 0, so if it has a degree of 1, 2, 3, 4, 5, and we learned in the previous lesson that the degree comes from the highest exponent on a polynomial function, that function is always going to have a number of 0 roots. So the number of roots or solutions or zeros, which we'll talk about in a second, is always going to match the number that the degree is. So for example, over here on the right, I have a polynomial function that's 4x cubed plus 2x equals 14. Well, if I wanted to put that in standard form, I don't even have to, because I know that the degree means what the exponent is when it's on the highest exponent. So that tells me the degree is 3. And since the degree is 3 here, that tells me that the number of zeros is going to be 3. So the fundamental theorem of algebra always says that those two will match up. Okay, so kind of what I just said, the next box just is saying all the different terminology for these zeros or roots or solutions. We are looking for where the graph crosses the x-axis. We've talked about that already. Those are zeros. It's the roots sometimes you'll hear, or the solutions to the equation, because that's where f of x is equal to 0, and that's where we find our zeros. Okay, so we're going to talk in 1.5 and 1.6 about how to solve these polynomials and how to find the zeros and so forth. But the first thing we're going to do is talk about a couple of refresher things, hopefully, but maybe not. The first one is the remainder theorem. Remainder theorem is basically long division. We can think about this as long division. What this says is that if we take the quotient times the divisor, and the divisor is always the one doing the dividing, plus the remainder, that will be equal to the dividend. So if we work backwards, we can also say that if we take the dividend and we divide that by the divisor, that's divisor, sorry, we should get the quotient, which is our answer, and then in the bottom here, we always get the remainder. They're saying the exact same thing, just two different ways. So we can use this to our advantage, and we can use the fact that we can take polynomials and divide them to figure out what the remainder is. And if there isn't a remainder, we'll see in a minute here, that we can then say that that is a factor of the polynomial. So if I'm asked to find the remainder after I divide the f of x, x cubed minus 4x squared plus 2x minus 5, by the dividend, or the divisor, the one doing the divisor using long division. So the first thing I'm going to do is I am going to put the dividend underneath the long division. That's always my first step. I have to set this up so I can do the long division. So I have x cubed minus 4x squared plus 2x minus 5, and I'm going to divide all of that by the divisor, which is x minus 3. And I'm going to do exactly what I would do using long division. Now the steps are the exact same, where I have to divide, multiply, subtract, bring down, okay? But now when I go to figure out what I need to divide, how I kind of look at it or think about it is I ask myself, what do I need to multiply x by in order to get x cubed? And when I figure that out, I put the number on the top because that's going to be part of the quotient. So x times x squared, that goes up top, is what I would need to do and multiply to get x cubed. That's the first step. Then I go ahead and I multiply. And when I multiply, I'm going to go ahead and make sure to multiply the x squared by both parts in the divisor, because it's being multiplied by not only the x to get x cubed, but also the minus 3 to get negative 3x squared. Now, if you recall in long division, the next thing is we have to subtract to see what we have left over. So I would subtract the 2, but be careful, because when you subtract, you're actually subtracting every term in that next line, and it turns all of the signs the opposite. If you've done the multiplication correct, your first terms should cross off, making it one smaller degree. Now I can go ahead and subtract negative 4x, in this case plus, because it was minus a negative 3x squared, gives me negative x squared. That's the first step, and that's the step in the process, not the first step, the first process, and I'm going to repeat that over and over again until all of the terms in the dividend, the stuff in pink, are gone. So now I'm going to bring down the 2x, and I'm going to do the exact same thing. I'm going to ask myself, what do I need to multiply x by to get negative x squared? And in that case, it would have to be minus x or a negative x. And now I'm going to do my multiplication. But again, when I multiply, I need to multiply everything in that divisor by negative x. So negative x times x is negative x squared. Negative x times negative 3 is plus 3x. And now I'm at the stage of subtracting again. But when I subtract, I'm going to change the signs of everything in that next line, because it's subtracting a negative and subtracting a positive, so it changes the signs. If I've done it correctly, my x squareds will cancel out, and they do. And then I'm going to go ahead and add again, and I get negative x, and I have to bring down the negative 5. And I'm going to do this one more time. So now I'm going to ask myself, what do I need to multiply x by to get negative x? Well, the x is already there, so then it's just a number. So I'm going to multiply that by negative 1. So negative 1 times x is negative x, and negative 1 times negative 3 turns out to be a positive 3. And if I go ahead and subtract those two again, that's going to change the signs of both. X's will cancel out, and I will be left with negative 8. So how we write this answer then, okay, this says to find the remainder. So all I would have to do is write the remainder is negative 8. But if the question asked what was the quotient and remainder, then how we write this is you write the quotient, which would be the stuff on top. That's the first part of the answer. So this would be x squared minus x minus 1. And then you always write plus, or in this case minus because of the remainder, and then over the divisor. And that is the exact same way we wrote fractions once we came up with the long division. You would write what was on top and then the remainder over what was out in front. Okay, so that would be our final answer if they were asking for what the quotient would be. Okay, go ahead and try example 2 and 3. Try 2 and then play the video. See where you went wrong, try to find your mistakes and so forth if you made any, and then we'll go over 3. So go ahead, pause the video, take a couple minutes to try example 2 on your own using the same process as example 1. Okay, hopefully you had enough time. You paused the video and you gave it an honest effort. If you got stuck along the way, now you should be listening and trying to follow along with me. Again, making sure that you pause along the way as needed. So, first step, we are going to write it so that we have the dividend underneath, that's the f of x, and then we have the divisor, 3x plus 1, outside. Now, I ask myself, what do I need to multiply 3x by to get to 3x cubed? Well, I already have a 3 and an x, So therefore, I'm just going to have to multiply it by x squared. Now I multiply. When I multiply, I need to make sure that I multiply not only by the 3x, but also the 1. So therefore, I would get negative, or I would get a 3x cubed, and then I would get a plus x squared. But you will notice that my signs have changed because I'm subtracting both of them. Once I subtract, my x cubes will definitely cancel out. And when I have a negative 5x squared and I'm subtracting an x squared, I get negative 6x squared, and then I have to bring down the 10x. So now I'm going to ask myself, what do I need to multiply 3x by to get negative 6x squared? And the answer would be negative 2x. And then I need to go ahead and do the multiplication. Don't forget to multiply by the negative also. And I would get that negative 6x squared, and then minus 2x. But again, you'll notice how I changed both signs because I'm subtracting all of that. And when I do that, I end up canceling out the x squareds, and I get 10x squared plus 2x squared, which will give me 12x squared. So finally, I need to ask myself, what do I need to multiply 3x by to get to 12x? And that answer would be 4. And then I have to do the multiplication. And when I do the multiplication, I end up with 12x plus 4. But like I've said several other times now, both of those signs get changed so that my x's cancel out because I'm subtracting, and then I end up with negative 6. So again, the remainder would be negative 6, but just practicing on how to write my final answer like I have up here, I would go ahead and write the quotient, which is up on top. So I have the x squared minus 2x plus 4. And then I have the remainder, which is negative 6, and there's the negative sign. And then I have the divisor, which is out in front there. Okay? Hopefully you were successful, or you at least found your mistakes there. Now go ahead, pause the video, and try example 3. I'll give you a hint here. Make sure first, before you do anything, that in the dividend, you want to write that in standard form. And you want to write it so that all the terms are accounted for. Meaning, I'm going to rearrange f of x. This is the easiest way. I'm going to rearrange it so I write in standard form. So the biggest exponent is 3, and then I'm going to work my way down to the smallest exponent. Well, there isn't an x squared, so I'm going to go ahead and write that in because it's going to be a placeholder for me. And then I'm going to write the plus 4x, and then I have the minus 1. That's going to be the way you want to write that when you're writing the dividend. And if that ever happens in the divisor also, you would do that as well. But we don't have that here because it's just the x and then the x to the first power and x to the 0. So go ahead, pause the video now, and make sure that you are using this as your dividend. We need all placeholders, and we need them in standard form. Go. Okay, once you had that written, and I gave you the little hint, hopefully you were able to do the rest, just like examples 1 and 2. So first, I need to ask myself, what do I need to multiply 2x by to get to 2x cubed? And that's x squared. Then I'm going to multiply. When I multiply, I get 2x cubed minus 2x squared. Then I'm going to go ahead and switch the sign because I'm subtracting all those terms. That's probably the most common mistake that people forget to do, so be careful. If you got it wrong, check there first. Once I subtract, I get 2x squared, I bring down the 4x. What do I need to multiply 2x by to get to 2x squared? That would be x. So I put a plus x up there in the quotient. Do the multiplication. Don't forget, these signs were originally the opposite. I just went ahead and switched them because of the subtracting all terms. Once I subtract, I get 6x. I bring down the 1. ask myself, what do I need to multiply 2x by to get to 6x? And that turns out to be 3. Do the multiplication. I get 6x minus 6. Again, got to change those signs. And then when I subtract, I end up with a remainder of 5. So my final answer would be my quotient, which is again the stuff on the top, plus my remainder over my divisor. And that's how we come up with the answer. Okay? Now, the nice thing about that is we can use that to see if anything is a factor. So if I wanted to, if I didn't know how to factor something, which we'll talk about later, but if I didn't know how to factor something, I could always just keep dividing to see if it's a factor. Because if it's a factor, it's going to divide evenly, and that remainder is going to be 0. So if ever I end up with a remainder of 0 here, that means that 2x minus 2 is a factor of this, which means I could write it as 2x minus 2 times something else to get to this, okay? So we're going to use something called the factor theorem, okay? And this is going to help us so that we don't have to keep doing long division to see if something is a factor of a polynomial. Because trust me, long division is a pain in the butt. So we want to try to have as many shortcuts as we possibly can. So what the factor theorem says is that if x minus c is a factor, so if this right here was a factor, meaning I could divide a polynomial by that, just like I did up here, then it's going to be a factor of f of x if we get the remainder of 0. That's kind of what I was just saying, okay? So we're going to use that to our advantage because if that's the case, then this means f of c is 0. So if I just plug 0 in and I get, or if I just plug c in, and I get 0, then that means it's going to be a factor, okay? So here, I have a factor for number 1, for A, example 4a. The factor is x minus 1. Well, if that's a factor, then I need to see if x equals 1 is, in fact, when I'm f of 1, if that is 0, then it's a factor. If it isn't 0, then it's not a factor. So let's evaluate that. We've spent a lot of 1a evaluating functions. So let's go ahead and figure out what f of 1 is. Remember, f of 1, we just go ahead and plug this value of 1 in everywhere I see the x. So this is going to be 2 times 1 cubed minus 1 squared minus 2 times 1 minus 3. When I evaluate that, and you can use your calculator if you want, totally fine, but this becomes 2 minus 1 minus 2 minus 3. And if I do that, 2 minus 1 is 1, minus 2 is is 3, and then I get minus 3. This should be a plus. Sorry, there's a plus sign in there. That should be a plus 2, and then it's minus 3. So that should be 1 plus 2 is 3, minus 3 is 0. So yes, x minus 1 is a factor. Okay. Go ahead and try B. Pause it. You can either use the long division technique like we just did up above to see if your remainder is 0, or you can use the factor theorem idea saying that if you just evaluate it at that number, if it's yes, then that happens to be a factor. The question is, a lot of times, what do I plug in? Because here I saw a -1, but we plugged in a 1. So why is that? Well, that's because this is the factor over here. This is the 0. That's like your answer, your solution. So if you're looking at B here, and it's x plus 3, that's the factor that I want to see if it is in fact. So I need to plug in then x equals -3. So you're always plugging in the opposite, okay? Basically, you're setting x plus 3 equal to 0 and solving for it to see what your x value would be. So go ahead, plug that in, and see what you get. Okay, so I use the same technique as A. I went ahead and plugged in -3 everywhere into the factor, And it turned out I got negative 54 minus 9 minus 6 minus 3 equals negative 72. And because this is not 0, when we evaluated it at that 0 and we didn't get 0, that automatically tells me that x plus 3 is not a factor. Okay? Okay, example 5, same idea, only now you notice that we have a value in front of x. So that kind of goes back to what I was saying for b. If we want to figure out what we need to plug in to see if 3x minus 4 is a factor, I can go ahead, if I wanted to, and do my long division and do 2x squared plus 7x minus 20, divide that by 3x minus 4, do all of that work and see if the remainder is 0 or not. Or what I can do, same thing we did up above, but now I need to figure out what number to plug in. So if I set that equal to 0 and I solve that, that would be 3x equals 4. Divide both sides by 3. I need to plug 4/3 into that function. So I am going to see what g of 4/3 is. When I plug that in, I am definitely going to use my calculator because we have access to it, so I might as well. I could, if I wanted to, do the math, but that's going to be a really long video. So let me pull up my calculator here. And I'm just going to plug those values in. So 6 times, remember we enter our calculator, or fractions into our calculator by hugging them. So 4 divided by 3 squared plus 7 parentheses 4 divided by 3 minus 20. And I end up with 0. So g of 4/3 is equal to 0. So yes, 3x minus 4 is a factor of that polynomial. I think that's easier than long division, but if you liked long division, you absolutely can stick with it. Okay, go ahead, pause, and try B. Okay, first thing, we got to figure out what we're going to plug in. Turns out we would have to plug in negative 5/2. So once we plug negative 5/2 in, and I showed my math there, the numbers and all that stuff, plug it in your calculator. Just go ahead, hug the fractions, but here make sure that you do put negative 5 divided by 2. It's a negative sign, not a minus sign. Right? And if we square that, add 7 times negative 5 divided by 2, and then minus 20, oops, extra parentheses, we get 0. Okay? So definitely let your calculator do that hard math work for you. Okay, go ahead, pause the video, and try A and B. Again, you can use long division if you want to. If you do, don't forget, we need all terms accounted for, and I notice that I'm missing that x cubed. Sorry, I put the circle in the wrong spot. I'm missing my x cubed. It has to go to the 4th power, 3rd power, 2nd power, 1st power, 0 power, so you would have to include that. Otherwise, you just have to figure out what value you're going to plug in and evaluate. Go. Okay, taking a look at A, I went ahead and plugged in 1. Since x minus 1 is the factor, this tells me that I would have to have x equal to 1 and plug that in. When I plugged that in, I got 8, so no, x minus 1 is not a factor of that polynomial. And then for B, because it's x plus 3, that tells me that I have to plug in negative 3 and see if that is a factor. And it turns out also to be no. When I plugged negative 3 in, I got 372. Okay, that is enough information for you to do your homework for tonight, but I do just want to talk about one more thing with those degrees and multiplicities. There's a really interesting fact and kind of phenomena out there with polynomials that has to do with the degree on each of the individual factors. Okay, so the degree is the same thing of multiplicity is the same thing as kind of individual degrees on each factor. So you will notice here, if I'm looking at example 1, I have this imaginary exponent on the factor x minus 3 of 1, and I have another exponent, imaginary exponent, on the factor of x plus 2. You will notice on graph 2 that I have this exponent already on that factor of 2, and you will notice that on the graph 3, I have these exponents of 2 and 1. Okay, so the interesting thing at each of these is that if the degree or the multiplicity of each factor is the same, there is a pattern that happens every single time. Okay, so if we take a look, x minus 3 would give me a 0 of 3. Let me do a different color here. So at 3, we said the multiplicity was 1 because that's the exponent. And I notice that at that point, it's kind of crossing the x-axis. Okay. Now, if I take a look at the other 0, and I look at negative 2, the multiplicity is again 1 because of that imaginary exponent of 1. And I also notice that this crosses the x-axis. So at both of those zeros, when the factors had multiplicities of 1, they both crossed or passed the x-axis. Now let's see if that's the same thing with a multiplicity of 2 like we have in graph 3. So graph 3, I have a 0 of 5. I have the factor of x minus 5. I have the 0 of 5. The multiplicity, we said, was 2. And you'll notice it doesn't cross the x-axis. What ends up happening is it touches the x-axis and then kind of bounces back up. So some people, mathematicians, like to say that it's tangent at that point, and we've talked about tangent only touching the line one time. I say it bounces off the x-axis. Right? And that's exactly what we're going to say here. And I'm just going to do that for abbreviation since I already wrote it up above. Okay, go ahead and try to find for graph 3 the zeros, the multiplicity, and describe what's happening at each of those zeros. Pause the video. Okay, so one of the zeros is at negative 4. So if I take a look here, I have negative 4. At negative 4, that factor would be x plus 4. So that's a multiplicity of 1. And what's happening there is that it's crossing the x-axis. So exactly what we said in graph 1. Then I have the other 0 at 1. And the multiplicity there happens to be 2. And what ends up happening is that it bounces right off that x-axis again. Okay, go ahead and do the exact same thing with graphs 4 and 5. Pause the video. Okay, if we take a look here, if we look at the 0 here, there's only 1 for graph 4, and that's at 0. And the multiplicity there ends up being 3. There aren't any parentheses, but you could put parentheses if you wanted to. Now, does that cross the x-axis or bounce off the x-axis? The answer is neither. What ends up happening is that it passes through, but it also has like a little wiggle effect. So yes, it kind of crossed like we had with a multiplicity of 1, but I think of it as like it crosses with some pizzazz. Okay? So go ahead and try graph 5 now, and notice that I do see a multiplicity of 2 here, and a multiplicity of 3. So let's see if those patterns continue from what we've seen with graphs 1 through 4. Okay, first 0 is -1. And with -1, we have the multiplicity of 3. And if you notice, similar to graph 4, it wiggles through. The other 0 turns out to be at 2, and that is a multiplicity of 2. And what ends up happening is it bounces. So here's our summary. We have the bounce, cross, and wiggle. Anytime we have an even multiplicity, so when we had in graph 2 with a 2 there, when we had it in graph 3, a 2, we had it in graph 5 with a 2, every single one of those at that 0 is always going to be tangent to the x-axis, like I said, real mathy. Or what I like to say is it bounces off the x-axis. Okay. Then, if there's a multiplicity of 1, that's when it's going to pass through or cross the x-axis. So we have a bounce, we have a cross, and then the last but not least is when we have an odd multiplicity greater than 1, like we had here in graph 5, like we had here in graph 4. If it's to the 3rd power, to the 5th power, to the 9th power, to the 19th power, any odd multiplicity greater than 1, that is when it's going to cross the x-axis for sure, but it's going to wiggle through it a little bit. It's going to have a little bit of that pizzazz that goes with it. Okay, that is all we're talking about today. Hopefully you learned some new stuff, but you also reviewed some stuff. Again, the thing I like about videos is that you can re-watch them, pause them, slow them down, speed them up, whatever you need to get a better understanding. So remember, put the work in. Might have to re-watch this, but that's okay because you want a good understanding. If you have any questions, let me know.